Okay, so chapter 11 is all about Young modulus. Now, what is Young modulus? Young modulus is a value that tells you the stiffness of an object, which means if you have an object with a greater Young modulus, that means it is harder to reform. Okay, you need more energy, more force, more work need to be done to change the shapes. Okay, it's harder to change its shapes. So in chapter 11, all right, in chapter 11, it begins with two things. The first one is what we call stress, and the stress is sigma equals to F over A. This is the equations. So basically, you're looking at the pressure that is being exerted on something. And then we have another thing called strain. Strain is the ratio, okay, epsilon equals to the ratios of elongations over original length. Okay, we have an E over L. So this elongation, sometimes students like to call it extension. The change in the length, whether it gets longer or it gets shorter. So now what is F, what is A? Now that is the things that you have to be extra careful. Now let's say if we have an object, this is an object, this is the road, okay, or this is a strings. Now if we pull an object, okay, if we pull an object, the force is being exerted parallel to the strings. Okay, this is the directions of the force. And that's why in a Young modulus, when it comes to stress, most of the times we use tension, okay, tension inside the string. Because when you pull something, the force that's being exerted on the strings, on the rope, okay, that is our tension. And remember, if you want to calculate the stress, the area is not the surface area of the whole object, the whole strings. So you don't calculate the surface area of a cylinder. What you have to do, you look at the diagram, you look at your object, you try to identify the area that is perpendicular to the force, which in this case, the area perpendicular to our force is just a circle right here. So this is the area that we're going to use in our calculations. So remember, okay, I repeat, area is not the total area of the string, it's not the total area of the object. Okay, but we are just going to use the area, the cross-sectional area of the object. Now, what is the cross-sectional area? It's the area that is perpendicular to our force, which in this case is a tension if you are looking at the road. Okay, so remember, area is always perpendicular to the force. All right, so that is a stress. So what is a strength then? Now, strength we say elongations over original length. So before you pull something, before you exert the force on this rod, the length is what we call L naught. After you pull it, okay, maybe it will extend just a little bit. Okay, but that little bit itself, that is the elongation. That is enough for us to calculate the strain. So the extensions here, okay, the elongations here, the additional lengths here, this is what we call elongation. So epsilon equals to E over L naught. And when you combine these two equations, okay, then you will be able to calculate the Young modulus of the object. So you combine these two equations, then you obtain a new equations called called Young modulus. Sorry. So Young modulus, the equation is equals to sigma over epsilon. But most of the times, okay, we seldom use sigma over epsilon. Most of the times we use equations that we already derive it. Okay, we already sub the equations of stress and strain, and now we derive new equations. So sigma equals to F over A divided by E over L naught. So you rearrange the equations, you will obtain Y equals to, okay, Y equals to what? Y equals to F F L naught over AE. So most of the time, this is the equation that we use in our calculations. So if you have a higher Young modulus, if an object comes with a higher Young modulus, means it is more stiff. Okay, it is harder to deform. Okay, so okay, that's it. Okay, that is a Young modulus. So from Young modulus, you can then calculate the energy stored inside the object, which is called strain energy. So strain energy, the equation is just simply equals to, okay, let's say this is U equals to 1 over Fe. Okay, 1 over Fe. So strain energy is just apply the equations, or you can calculate it from the F against E graph. So in this chapter, you have two graphs. The first one is stress against strain graph, and the second one is F against E graph. Both of them, they have same shape, but they serve a different purpose. Okay, one you use it to calculate strain energy per unit volume, another one you use it to calculate the strain energy. And of course, based on the graph, you should be able to identify, okay, which part of the graph undergoes plastic deformation, which part of the graph undergoes uh, elastic deformation. Okay, so that one I will leave it to you. The details explanation is in your lecture notes. All right, so now we are done with the summary. Now let's proceed to exercise one. Let's proceed to the questions. So questions one. A sign hangs from the end of a vertical steel girder with a cross-sectional area 0.012 meters squared. Given Young modulus for steel is equal to 20 times 10 to the power of 10 Pascal, what is the stress within the girder? So you want to calculate stress. This is a very straightforward question. So questions A, now you want to calculate stress, and we know that stress sigma is equals to F over A. So what is the F in these questions? So now let's see. You have a girder. Okay, basically it's just a string-like object. So you have a string here, and then there's a sign that is being hung on at the ends of the string. Okay, so this is a wall. Okay, let's say this is a ceiling, and then this is a strings, and then you hang a signboard here with a mass equals to 1,700 kg. So how are we going to identify the force? Okay, the force that we're going to use in our equations. First of all, let us begin with a diagram. Okay, a free body diagram. So free body diagram for this object. Now we have a W going downwards, and then we have a tensions going up. Okay, T going up. And then, according to the questions, now what you want to calculate is a stress within the girder, which means within inside the string. In other words, the force that we want to use in our calculation is the tension, because now we want to see what happens inside the string. Therefore, every information, every piece of information, everything that we want to use in our equations, it should be coming from the string, which is the tension. So tensions, okay, according to the free body diagram, since now my object is not moving, I'm going to use Newton's first law, okay, to identify, to determine the values of tension. So summation F equals to 0. Based on the free body diagram, we have T equals to W, which is equals to mg. So from here, we can then determine the values of tension. Okay, so T equals to 1,700 times 9.81. Therefore, we have a tensions. Okay, wait here, let me calculate first. So 1,700 times 9.81. So I have the value equals to 16677 Newton. Okay, so that is the values of tensions based on the free body diagram. Okay, based on our free body diagram. Then how about the cross-sectional area? So this question is being very nice to you. Straight away, give you the cross-sectional area already. Okay, you don't have to calculate it. So basically, sigma is then equals to 16677 divided by 0.012. So the final answer is 1.39 times 10 to the power of 6. Nm negative 2. And of course, if you want to use Pascal, go ahead. Okay, both are correct. So both are accepted. So that is the questions A. Okay, questions A, sigma equals to F over A, and the final answer is 1.39 times 10 to the power of 6. So based on the diagram, since you want to calculate the information inside the girder, therefore you use the force that is being exerted on the girder, which is the string. So the force that is being exerted on the string is known as tension. Therefore, we use tension in our calculations. Okay, then how about questions B? Questions B, the strain. Okay, the strain. So how are we going to calculate the strain? If you look at the equations, epsilon equals to E over L naught. Now, obviously, you cannot use these equations. Why? because we don't have the elongation. And if you look at question C asks you to calculate elongation, which means we cannot use this equation to solve questions B. Then other than this equation, which equations can we use? Okay, what else can we use to calculate the strain on the girder? So other than these equations, epsilon equals to E over L naught, another equation that can be used obviously is Y equals to sigma over epsilon. So can we use these equations? Now try to think. Do we have Young modulus? Yes, we do. Young modulus is given, which is 20 times 10 to the power of 10. Then do we have a stress? Well, yes, we do as well, because we already calculated in questions A. All right, which means these equations can be used to solve questions B. Now let's substitute the value. So y is equals to 20 times 10 to the power of 10. Then it is equals to sigma. Sigma is 1.39 times 10 to the power of 6 over epsilon. Rearrange the equations, then you should be able to obtain 6.95 times 10 to the power of negative 6. So that is the answer. And remember, when it comes to strain, okay, it is a dimensionless. Okay, no dimension, no unit. Why? Because when you use elongations divided by original length, the unit is being cancelled out. Okay, therefore, strain is a dimensionless quantity, a value without unit. Okay, a quantity without unit. So that is how you solve questions B. Okay, that is how you solve questions B. So when it comes to question C, then how to solve question C? It tells you the original length is 9.5. You are given original length. You want to calculate elongations. You have strain from questions B. Straight away, you can apply equations. Okay, now let's see. Where should I write it? Okay, I'm going to write it here. So question C, epsilon is equals to elongations over original length. So you have epsilon, which is 6.95 times 10 to the power of negative 6. And then it is equals to, okay, wait, yeah, I'm going to draw a line here. Okay, so it is equals to elongations divided by the original length, which is 9.5. Rearrange equations, elongation is equals to 6.6 times 10 to the power of negative 5 meter. All right, meter. So that is the final answer for question C. Okay, so these questions actually is very simple. It tests whether you understand what is stress, what is the strains, and what is the relationship between stress, strains, and also Young modulus. Okay, so now I give you 2 minutes to write down everything, including the summary. Okay, so you write down the solutions, you write down the summary before we proceed to questions number 2. Okay, 2 minutes from now. Okay, so now let's look at questions 2. Okay, questions 2. A 15 cm long tendon, now you're given a length, okay, which is L is equals to 15 cm, L not original length, was found to stretch 3.7 mm. So this is elongations, and if you notice, both quantity, they have different unit. So be extra careful with the unit, all right, when it comes to original length and also elongations. Usually they have a different units. Why? Because the elongations usually comes in a very, very, very small values. Okay, so be extra careful with the unit. So by a force of 13.4 Newton, so you have a force, and the tendon was approximately round with an average diameter. So you are given diameter. Now why? Why you need diameter in these questions? Okay, why questions give you the values of diameter? Well, because you want to calculate the area. So whenever you are given diameter, it means you need to calculate the cross-sectional area. Okay, you need to calculate the cross-sectional area. So given D is equals to 8.55 mm, calculate the Young modulus of this tendon. So in this question, it assumes tendon is a cylinder-like object. Okay, so this is your tendon. And then you're given the original length, L naught equals to 15 cm, which is equals to 0.15 meter. All right. And then the elongations, so you stretch it. So this is the elongation, this is the extension. So elongation is equals to 3.7 mm, which is equals to 3.7 times 10 to the power of negative 3 meter. So I would suggest you all to change everything into SI unit first, okay, before you solve the questions. So you jot down all of the information, you convert it into SI unit before you apply the equations. So elongations, E is equal to 3.7 times 10 to the power of negative 3 meter. And then given force, okay, so this is the force, which is equals to 13.4 Newton. Okay, 13.4 Newton. So your first task, your first job is to calculate the cross-sectional area. Since you are given D equals to 8.5 times 10 to the power of negative 3 meter, and A is equals to, now A is either equals to pi r square, and if you don't want to calculate a radius, you can straight away use a pi d square over 4. Okay, because r is equals to d over 2. If you square d over 2, then you obtain d square over 4. Therefore, a is also equals to pi d square over 4. So now I'm going to calculate the area first. So it is equals to pi, and then d, I have 8.5 times 10 to the power of negative 3 square over 4. So area is equal to 5.67 times 10 to the power of negative 5 meter square. So that is the area. Okay. So yeah, any questions? Ada. Okay, so now that I have
No
A,
meeting. Thumbs up.
okay, so now that I have A, I can then calculate Young modulus. So Young modulus is equals to FL naught over AE. Okay, so this is what I told you just now. Most of the times we will straight away apply these equations rather than sigma over epsilon. So Young modulus is then equals to 13.4 times the original length 0.15 meter over A, 5.67 times 10 to the power of negative 5 meter square times the elongations 3.7 times 10 to the power of negative 3 meter. So remember, everything should be in SI unit. Young modulus is then equals to 5 point, 9.573 times 10 to the power of 6 and m negative 2, okay? Or you can use Pascal. Okay, so it's up to you whether you want to use Pascal or you want to use a Newton per meter squared. Both are correct. Okay, both are accepted. So that is questions number two. Okay, so questions number two just want you to be careful with the unit. Okay, they just want you to learn how to convert the units and what is the unit that you should use in calculating the Young modulus. Okay, so that is questions number two. I give you 2 minutes to write it down before we proceed to questions number three. Okay, so 2 minutes for you to write it down before we try questions number three. All right. So now let's look at next question. So these questions, it requires a bit of knowledge from chapter 4. Okay, so well, we'll try these questions and also as part of the revision for our chapter 4. So an object of mass 3 kg is suspended from a steel cable of a length 40 meter and a cross-sectional area. So now you're given mass, you're given the length, and then you're given the cross-sectional area. Determine the extension, which is the elongation, the E of the cable. When the mass cable system is at rest, it moves upward at a constant speed. It moves downward at a constant acceleration. So now let us sketch a diagram. So this is a cable, and this is an object. Okay, this is an object. And then this object comes with a mass, right? So you have a hanging object, and now this object is moving. And according to the questions want you to calculate the extensions of the cable. So again, you're looking at what happened inside the cable, which means the force that we should use in our calculation, once again, is the tension, right? So tension should be used in our calculation. So how are we going to determine the values of tensions then? Now, since we're not given the tensions, what we have is just the mass of the object. So let's sketch a free body diagram for this mass cable system. Free body diagram for the object. Okay, so object M. Okay, object M, it comes with a mass. So whenever you have a mass, then that comes with a weight. Okay, and then there's a tensions that is going upwards. Questions 8. Okay, questions 8. Now your object is at rest. If your object is at rest, then what should you do? You're going to apply Newton's first law. Okay, for object that is not moving, for object that is at rest, you apply Newton's first law. So if object is not moving, then straight away the upward force is equals to downward force. Therefore, T is equals to W. It is equals to mg, right? So it equals to mg. Therefore, T is equals to 3 times 10 to the power of 3 times 9.81. So that is the value that you should use in questions A. That is the tensions in the questions A. So 3 times 10 to the power of 3. Okay, let me calculate first. 3 times 10 to the power of 3 times 9.81. So we have a 29403. Okay, we have a 30 Newton. So that is the tensions for questions A. Now that we have tensions, we can then calculate the extensions by applying Young modulus equations. So y equals to FL naught over AE. So given Young modulus is 2 times 10 to the power of 11, so it is then equals to, now force, again, force inside this cable, it refers to the tension. Okay, so we have tension 29430, and the initial length 1 times 10 to, initial length is 40. Okay, initial length is 40 divided by cross-sectional area 1 times 10 to the power of -4, and then the elongations, the extension is the things that we want to calculate. So now rearrange the equations. E is then equals to 5.89 times 10 to the power of -2 meter. All right, so that is the answer for questions A. Then how about questions B? So questions B, again, you have an object that is moving at a constant speed. Okay, so at rest and at constant speed, when we have these two cases, when you are given these two cases, then it means we are going to apply Newton's first law. Okay, so for questions B, since my summations F is equals to 0, so again, my T would be equals to 29430 Newton. Okay, so if T equals to 29430 Newton, you apply equations y equals to FL naught over AE. Then once again, E is just equals to 5.89 times 10 to the power of -2 meter. All right. So remember, if your object is at rest or if it's moving at a constant speed, then you apply Newton's first law. Then how about question C? Now, question C, you have an object that is moving, but it is not moving at a constant speed anymore. It is moving at constant acceleration. So if your object is moving at constant acceleration, then you need to apply Newton's second law, which is summations F equals to ma. And it says moving up. So if your object is moving up with an acceleration, then it means we are going to take upward as a positive direction and downward as a negative direction. So if you expand the equations, then the equations will be T minus W equals to ma, then T minus mg equals to ma. And therefore, T is equals to ma plus mg. So this is how you calculate the tensions in question C. Okay, so it is then equals to 3000 times 3 plus 3000 times 9.81. Therefore, T is then equals to 38930 Newton. Okay, 38930 Newtons. So once that you have the tensions, you can then apply Young modulus equations to determine the values of extension. So y equals to FL naught over AE. Y equals to 2 times 10 to the power of 11 is then equals to, now force is a tension, so it is equals to 38930 times the initial length, which is 40 meter, divided by 1 times 10 to the power of -4 E. Okay, so rearrange the equations. E is then equals to 7.69 times 10 to the power of -2 meter. Okay, so 7.69 times 10 to the power of -2 meters. So this is the final answer. All right, this is the final answer. So now again, I give you 2 minutes to write it down. The crucial part in this question is to see, to test whether you know how to determine the tensions or not at, at various situations. Okay, that's why if you look at the questions, you have the situations, you are given the situations where the object is at rest, it is moving at a constant speed, and it is moving at a constant acceleration. Three different situations. Okay, so you need to know how to determine the tensions at three different scenarios. So 2 minutes for you to write it down. Okay, so make sure to write it down why the summation is equals to 0, why summations f is equals to ma, and how to determine the values of T, of tensions. Tuh dia. Okay, so if done, then let's proceed to the next questions. So questions number 4. Questions number 4, the wire has a mass of 10 grams. So if you look at the values given, once again, it's not in SI unit. So this is M. So M equals 10 gram, which means it is equals to 10 times 10 to the power of negative 3 kg. And then length is 2.5 meter. So this is your L node. So given force F equals to 100 Newton is applied to the wire, and it then extends by 2.3 mm. So this is your E. Determines the Young modulus of the metal wire. So if you look at these questions, okay, you have a length, you have force, you have elongations. But then one thing is missing. Okay, if you want to calculate Young modulus, now let's see. Equation for Young modulus is y equals to FL naught over AE. If you look at these equations, okay, one thing is missing. The thing that is missing, the information that is missing is area. We don't have area, then how are we going to determine the values of a Young modulus then? Okay, now, if you look at the questions again, okay, sometimes if you couldn't find the information from the main questions, okay, then you try to read the questions until the end. So questions B is a strain energy stored in the stretch wire. And the last part, okay, last part of the questions, you are given a value called density. So given the density of wire, rho is equals to 2.7 times 10 to the power of 3 kgm negative 3. Aha, so what is the purpose of density? Try to think. So if you look at the questions A again, area is missing, cross-sectional area is missing, and you are given the values of density, then that it must be something that can be used to calculate the area, right? The cross-sectional area. So density rho, we know it is equals to m over v. Okay, so you have a wire, the shape of the wire is a cylinder. Okay, when it comes to the shape of the wire is a cylinder. So cylinder and a rho, what is the relationship things again? Now you have a quantity called V. How to calculate, how to determine the volumes of a cylinder? So volumes of a cylinder is V equals to A times L. So we have L naught. The thing that is missing is the area. So which mean density can be used to determine area. Why? Because rho at the same time is equals to m over a L naught. Okay, so because the volumes of a cylinder is equals to cross-sectional area times the length, therefore we have V equals to a L naught. Okay, so you sub a L naught into the equations of density. So rho is equals to m a L naught. Sub the value again. 2.7 times 10 to the power of 3 equals to, given n is equals to 10 gram. So 10 times 10 to the power of negative 3. divided by A, and original length is 2.5. So rearrange the equations. Area is equals to 1.48 times 10 to the power of negative 6 m squared. Okay, so this is how you determine the values of an area. Now that you have A, you can then calculate the Young modulus for the metal wire, for the metal of the wire. So Y is equals to, given first 100, L naught 2.5 over A, 1.48 times 10 to the power of negative 6, and then the extensions 2.3 times 10 to the power of negative 3 meter. So, okay, so be careful. Make sure everything is in SI unit, all right? So a Young modulus is then equals to 7.34 times 10 to the power of 10 Pascal. All right, so that is how you calculate, that is how you solve questions A. So the crucial part is on how to calculate, how to determine the values of cross-sectional area if you are given density. Okay, if you are given density. So this is how you solve it. All right, this is how you solve it. So first of all, you need to know the shape of the object. So if you're talking about wire, if you're talking about strings, then usually we assume the shape is a cylinder shape. Okay, it's a cylindrical shape. So if you have a cylinder, volume is equals to cross-sectional area times L. All right, cross-sectional area times L. So from here, you then determine the values of cross-sectional area. Okay, or you can even use this method to determine the original length of the object. Okay, if you are given a cross-sectional area, then you can rearrange the equations and obtain the original length. So questions B. Questions B is strain energy. So strain energy, we have two equations. The first one is U equals to 1 over 2 Fe. And then the second one is U equals to 1 over sigma epsilon V. Okay, the volume. So now let's look at the questions. Questions, okay, given F and E. So which means it will be easier if you use the first equations. Since you are given the force, you are given the extensions, the elongations. So U is equals to 1 over 2, 100, and then 2.3 times 10 to the power of negative 3. Okay, so U is equals to 0.115 joule. All right, so questions B is just a very simple and straightforward questions. You just have to know which equations to use. All right, which equations to use. Okay, so B done. So again, I gave you 2 minutes to write it down before we proceed to the questions 5. Okay, the last questions for today's class, for today's sections. Okay, so now let's look at questions 5. So questions 5 is quite similar to questions 3. Okay, you need to apply Newton's law to determine the tensions in the wire before you solve it. So an object P of mass 0.5 kg hangs on a vertical tungsten wire of diameter 0.22 mm, and the length of a 1 meter hang from the bottoms of P is a copper wire of diameter 0.5 mm. So this diagram, okay, now let us sketch the diagram first so that we can visualize what is going on. So let's say this is a ceiling, and then you have an object P, okay, that you hang with a tungsten wire. Okay, so this is your object P. And then after object P, okay, so this is a tungsten wire. So after object P, there's another object known as object Q. Okay, and you hung it below at the bottoms of the P. And now you're using a copper wire instead of a tungsten wire. So this is what is going on. Okay, this is what happens in these questions. So assume the elastic limit of both wires is not exceeded, and both wires they are massless. Given tungsten wire, the modulus of tungsten wire is 3.6 times 10 to the power of 11, and the Young modulus of a copper wire is 1.2 times 10 to the power of 11, and G is equals to 9.81 ms negative 2. So sketch and label the free body diagram of object P and object Q. So questions A asks you to sketch free body diagram. So let's look at object P first. Okay, object P. Free body diagram, free body, a diagram without body. So a diagram without body, you use a dot to represent the object. So this is object P. Now object P is an object. Every object comes with mass. Whenever something has mass, means that it comes with weight. Alright, so we have a weight that is pointing downwards. Okay, now let's look at the diagram. If you look at the diagram, there is a strings above object P. So which means there's a tension. Okay, there's a tension that is going up. So T tungsten. Okay, T tungsten, TT I'm going to call it. And then if you look at the diagram again, other than a tungsten wire, okay, there's another wire that is being connected directly to the object P, which is copper wire. Okay, so which means there's another tension that is pointing downwards, TC. So TT going up, TC going down, and W also pointing downwards. So that is a complete free body diagram for object P. How about object Q? Okay, let's look at object Q. Now object Q, once again, it is an object. Every object comes with mass. Whenever it has mass, it comes with weight. So you have a WQ that is going downwards. Okay, so if you look at the diagrams, again now, there's a string being attached to object Q. Okay, so it means there's a tensions. Okay, there is a tensions acting on the object. So tensions copper. Okay, TC is going up according to my diagram. So I have a tension that is going upwards, and I'm going to label it as a TC. Okay, because now you're looking at copper wire. Okay, so now that's it. Okay, that is a complete free body diagram for object P and object Q. All right, let's look at questions B. So questions B asks you to determine the tension in both wires. So basically that is chapter 4. Okay, that is something that you have learned in chapter 4. You have two free body diagram, one for object P, one for object Q. You're not given the values of the tensions. You don't have T tungsten, you don't have T copper. But what you do have, you have two free body diagram. If you have two free body diagram, it means you can form two equations, right? So object P, okay, equations from object P. Now let's see. Now since both of them, they are not moving. If they are not moving, they are not at rest, means you're going to apply Newton's first law. So summations F equals to 0. So according to my free body diagram, okay, TT is equals to WP. Okay, WP plus TC. Okay, TT equals to WP plus TC. So a TT can be written as MPG plus TC. But if you look at these equations, okay, you don't have enough information to calculate either tensions. Okay, you don't have the information to calculate DT. You don't have enough information to calculate TC. So let us pause. Okay, let us stop at here. So I'm going to label it as equations 1 because now I cannot simplify it anymore. So next, I will try to see if I can get any information from second free body diagram. So object Q, okay, object Q. So object Q, once again, it is not moving, therefore we are going to apply Newton's first law. Summations F equals to 0. Based on the free body diagram, TC is equals to WQ, and it is equals to MQG. Okay, so MQG now, do I have enough information to solve it? Yes, I do. Okay, because I have the mass of object Q, which is equals to 0.35 kg, and then given G is equals to 9.81. Okay, so from here, I can then obtain the values for TC. So TC is equals to 3.45 Newton. Okay, so now that I have tensions inside the copper wire, I can then calculate it. I can then use it to simplify the equations 1. Okay, to calculate the tension inside tungsten wire. So TC equals to 3.45. So from equations 1, TT is then equals to MPG plus 3.45. So given MP is a 0.5 kg. Okay, so 0.5 times 9.81 plus 3.45. So TT is then equals to 8.34 Newton. Okay, 8.34 Newton. So that is how I solve it. Okay, that is how I solve it. I start from a free body diagram for object P, and since I don't have enough information to simplify it, I then move on to the free body diagram for a second object. So from the free body diagrams of the second object, object Q, okay, I able to I managed to determine the values of TC, which is 3.45. I then use it to determine the values of TT. Okay, so TT is equals to 8.34. So that is questions B1. Okay, that is the solutions for questions B1. The tension in both wires tungsten and the copper wire. And the questions B asks you to calculate total strain energy. So strain energy is a scalar quantity. If question asks you to calculate the total energy, then what you have to do? So you just simply calculate the energy in a P and the energy in tungsten wire and also energy in copper wire. Okay, and then after that you just add them up. So scalar quantity is very simple. You don't have to look at the directions. You just add it, you just add the value. So U total, okay, U total is equals to U tungsten plus U copper. Okay, U tungsten and U copper. Okay, and then if you want to calculate the values, okay, you want to calculate the strain energy, then you need 1 over 2. Okay, now I'm going to call it tungsten, TT, and then E also T, elongations inside tungsten wire, plus 1 over 2 TCEC. Okay, if you look at the equations, I'm stuck again, right? Why? Because I don't have the E. I don't have ET, I don't have EC. So let us go back to the questions and see. Do we have enough information to calculate elongations? Okay, to determine the values of elongation. Well, elongations, I have two equations. One is epsilon equals to E over L naught, and another one is Y equals to FL over AE, right? So obviously, I cannot use the first equations because I don't have a strain of the wire. So this one is out, okay? This equation is out, which means I can try to use Young modulus equations to determine the values of E. So do I have enough information? Now let's see. Well, Y, well, yes, I do have Y. I'm given the Young modulus. And then I have a force, okay, because I already calculated in the questions. 1. Original length is given. I don't have area, but what I do have is a diameter. Okay, so if you remember the things that I told you just now, if you're given diameter, it means the questions wants you to calculate area. So which means you have area as well. Then yes, we can use these equations to find the values of elongations, okay, to determine E. So F equals to FL naught over AE. Okay, so for this question, it's a bit long. You need to repeat it for both a wire. So let us calculate it. So Y for tungsten equals to DT, L naught T, and then AT, ET. So everything is for tungsten. So Y for tungsten is 3.6 times 10 to the power of 11. This then equals to tensions for tungsten. I have a 8.34. Okay, 8.34. Original length given is 1 meter over area. Now area, because I don't have the area, I'm going to apply pi d square over 4. Okay, so pi d square, d is 0.22 times 10 to the power of negative 3 square divided by 4, and then times with the e. Okay, times with e. So rearrange the equations. Et is then equals to ET is equals to 6.09 times 10 to the power of negative 4 meter. Okay, negative 4 meter. So this is the elongation, the extensions in the tungsten wire. Okay, so let's repeat it again for copper wire. So YC equals to TC L naught C over AC EC. Young modulus given 1.2 times 10 to the power of 11 equals to, okay, now just now we calculate TC equals to 3.45. Original length given is a 1.5 divided by, once again, okay, you don't have the area, but then you can calculate it by using diameter. Okay, you can calculate it by using diameter. So I have a pi d. So given diameter, 0.5 times 10 to the power of negative 3 divided by 4, and then times EC. Okay, times EC. So rearrange the equation. EC is equals to 2.18 times 10 to the power of negative 4 meter. Okay, negative 4 meter. So now that I have EC, I have ET, I can then calculate the total strain energy. So U total is then equals to 1 over 2, 8.34 times 6.09 times 10 to the power of negative 4 plus 1 over 2, 3.45 times 2.18 times 10 to the power of negative 4. Okay, so U total is equals to 2.91 times 10 to the power of negative 3 joule. So that is the final answer. That is how you solve it. All right, that is how you solve it. So this question is a bit long. All right, so make sure you understand. All right, make sure you understand how to calculate it. So when it comes to total strain energy, basically you just add up the energy in every part of the wire, in every wire. So you have a tungsten wire, you have a copper wire, you calculate the energy inside tungsten wire, you calculate the energy inside copper wire, and then you just add them up. Then done, end story. Okay, so that's all for today. Okay, make sure to write down the complete solution. If you have any questions, you may ask. If no question, then you may leave the class now.